All right, let's get started. So just a 2-minute recap. Talk to each other, try to describe why chain replication works, how it walks from the start. So a write starts from the head and goes to the tail, and a read comes from the tail. Why does that work? Or check your polymarket. And I don't get anything for you setting up a polymarket account. There's no referral fees. All right, so who wants to explain it to me? Because I don't understand it.
Is it because by the time the tail has accepted it, by the time it can reach the tail, all the nodes have to have also accepted it?
Right, because it's a bucket brigade, right?
Yeah.
In other words, you get a bucket of water at the end, you have enough for everybody in between.
Yeah.
And that's exactly the right way to think about it. So you read from the tail, and you write to the head. And what is this guaranteeing us?
Goodness.
Strong consistency. And that's really the whole point, is that this is not necessarily the cheapest model, but it provides you with very strong consistency guarantees. And that's really what we're going to be drilling into today. Are these little short reviews useful or not? Because I can take them out if they're not useful. How many people want me to keep them? How many people want me to get rid of them? Okay. Well, the other thought that I had is I'm going to have to bring bribes now. So I have to bake cookies and bring cookies in to get people who are willing to explain it to me so I can understand it better. And I don't buy the cookies, I bake them. So the chain causes a total ordering of rights. Everything is serialized through the head. Everything is committed by the time it gets to the tail. But this does have the downside that it requires a fixed topology and a clear leader, which we talked about, right? There's some sort of a magical configuration manager in this. That's a problem that Paxos actually solves, but it doesn't work in, it's like a timing thing. It doesn't work in a system like this because we're just kind of implicitly assuming somebody else is dealing with it. And the way that we actually do that is we end up using a configuration manager like, oh, I don't know, Zookeeper, which is Paxos. So we can use a Paxos implementation to actually build our robust configuration manager and then use something like chain replication. Okay, if I'm going to do that, what am I going to just do Paxos? Chain replication is still easier. And it's easier in the common case. Paxos to what configuration to decide who the configuration manager is, or to keep the configuration managers balanced and organized well, is a smaller pocket of complication. The complexity is lower. I mean, I spent 4 lectures talking about Paxos. I spent 1 lecture talking about chain replication. And that's because it's easy to see chain replication. It's hard to see Paxos. So you've seen the worst, and now everything else is like, okay, well, we don't want to do that much work. We want to be lazy. What can we do instead? I'll get somebody else to build the Paxos-based configuration manager because I've already done it, because then you can just use Apache Zookeeper. And then I can build my chain replication on top of it. But what if you want something that's maybe faster because you need performance? When you're using a distributed database and you query it, is it the latest value? I actually touched on this a couple of times. It's the value at the time you read it, but depending upon the actual guarantees of the distributed database, it might not be the current value even when you read it, but it certainly isn't locked out from change the moment that message with the response is sent to you. It's just your model. In order to know, you have to know what the service guarantee is of the distributed database. So in chain replication, somebody says here, I've built chain replication. It's easy. You know exactly what it is. You have the latest answer from the tail. But again, as soon as that message is sent, another update can arrive in the tail, and therefore the message that you got with the value is no longer actually the current value at the time you receive it. This is the problem with working with networks, is there's this actual pause between sending and receiving. It's not instantaneous. I've been using this term consistent. I mean, if you want, I can actually write a complete state machine definition of what a consistent state is. Well, it kind of hand-waves it and says you define what the consistent states are. Why do you read all of that database stuff? That's because databases are the classic example of an instance where it has to be consistent, where they make multiple updates. Why did I start with two-phase commit? Because two-phase commit is the way that you provide consistency in something where it's not replication. It's changing linked values. These values are entangled, and they have to change together or not at all. I like the term entanglement because if you know physics, that's literally what happens here. From the visible outside world, they have to be consistent with each other. You have a positive value, you have a negative value. And this is what happens in physics, right? Is you take nothing and you create a positive value and a negative value and then you separate them. But you don't know which one's the positive and negative value until you look at it. That's why they call it entanglement. And by the way, we build quantum networks now. Quantum networks are based entirely on entanglement. But here, this is just data entanglement. You put something, you buy something. We have to take it out of inventory and we have to add it to your order. So we take it out of one place in the database, we add it to someplace else in the database, great. But underneath that, the database is also updating physical state, actual persistent state. And you have to make sure the state is presented externally in a way that doesn't expose the fact that there are inconsistent states in the middle. And that's what I mean when I say consistent. But now what we're doing is we're generalizing this. The consistency model is literally the agreement between the source and the sink of what is guaranteed about that value. Consistent cuts. When we did consistent cuts, it wasn't yet the most recent value because we couldn't literally stop the entire world and grab a snapshot. It just wasn't possible. So what we said was, as long as we show you a view of the world that could have actually happened, we're going to call that consistent. But it's not strongly consistent, it's weakly consistent. Paxos and chain replication give you strong consistency. So the idea is that if you do things in a particular order, this is what you're going to actually see. Different contracts, different prices. And literally that is the standard trade-off in the industry, is that if somebody's giving you strong guarantees, they're generally charging you more for it because it's a lot more complicated, it requires more brain power to build it properly, it's harder to debug, it just has a whole series of complications that have nothing to do with technology and everything to do with, my gosh, this is why we pay those people so much money. I mean, how many of you are angling for $1 million a year or more jobs? Now, if somebody offered you one, obviously that's a different thing, but I can tell you the people I know who work in those kinds of jobs work really hard and are very smart and solve these kinds of problems. If you grab the slides from online, this is a little bit different than the slide online because when I was looking through it this morning, which is what I always do to make sure that it's looking okay, it didn't look good, so I had to change it a little bit. It's not radically different, but this one's just clearer, and it's something I'll update it. So what we actually have is a continuum of consistency models. We have linearizability, sequential consistency, causal consistency, and eventual consistency. So causal consistency is basically what you get from the consistent cut model. You see cause and effect in an ordered fashion, but you don't necessarily see it in the ordered fashion it actually occurred in relative to other things that were changing at the same time. Linearizability is what we spend most of our time on thus far. The last, 3 weeks, we've been talking about Paxos, we talked about chain replication, and those are linearizing systems. They literally say, this is the order everything happened in. But we can weaken it a little bit. We can say, this is the order it happened in on the local node. But it's not necessarily the order it happened in across the nodes. So this is no longer linearizability globally, it's just local linearizability. And globally, well, we can shuffle things around a little bit. That's weaker, but still pretty strong. And in fact, this is often where people end up compromising. I'll take sequential consistency. I won't see reads and writes out of order on an individual node. I won't necessarily see the order in which they happened on different nodes. Causal consistency is weaker still. It just simply says that I'm never going to see a read return something before the write occurs when it actually happened in the opposite order. So I will always see the reads and writes ordered relative to each other, but it's not even necessarily the same as the order in which it happened on the local node. Okay, so now you keep relaxing these things. We still have a little bit of order left over, but it gets harder to reason about when you're building your service on top of this. So I guess that's kind of an interesting way of thinking about it. I never really thought of it that way, but the cheaper service means that more of the cognitive load is shifted to the client, the customer, than it is shifted to the developer, the person who provides the service in the first place. And then the crazy one, the one that's actually quite fun to play with, is what's called eventual consistency, which says, you know, if we stop any new writes, eventually the system will catch up and everything will be consistent. But at any point in time, so the joke in the industry is literally that eventually consistent means never consistent. It's more of the, it's close enough. I mean, don't you have homework assignments or tests where you finally get to the end and you go, it's close enough, I am so done with this, I'm moving on. It's the same thing. It's the same basic principle, which says, this is good enough. It's not perfect, sometimes it's going to be wrong, sometimes I'll have to clean up messes, but it's faster, it's cheaper, and it's the best I can do right now. So this gold standard, linearizability, which is what we've been reaching for, is literally every operation is yes.
Where does strong consistency go through this? Like, I've heard that term, but it's not listed.
Strong consistency is either linearizability or sequential. Okay. Typically it's linearizability, but that's the problem, is that people can use slightly different terminology here. But it's definitely not on the causal or eventual consistency end of the spectrum. And people will say all sorts of anything, all sorts of things. You can hear what they say about you.
Oh, I hear it. I have big ears.
Well, that means you're important enough for them to talk about. Nobody talks about people who aren't important enough to talk about. This gives us the appearance universally, globally, no matter where you are, every observer can see the same exact thing at the same instant in time. It looks like it's running locally. This is literally why this is the strong case. It's the same exact behavior you would get if you ran it on your machine with one core. There's no parallelism, there's no ability for the ordering to change. Now, that doesn't fix the observability problem, which is you call somebody who's going to give you the right value at the time they return it, but then it's stale by the time you get it. And we have different ways of fixing that problem. We're not going to fix it at this level. Somebody has to fix that at a level above. When you start using real databases, what happens is you create locks. So you lock other people out from doing things. But there's reasons not to do that, and it's even more complicated. But we don't have to talk about that. You can keep that one for 504, those of you who ever take it. Anybody going on to grad school? There we go. I mean, sometimes when people can't find jobs, that's what they do. They just say, well, I'll just stay in school another couple of years. And then you get really caught into it and you say, oh, what the heck, I'll just go spend 8 more years of my life and get a PhD and then not be employable anyway. So what this means is that if a write completes before a read, then the read will see that write. That's basically it. The guarantee is when a write finishes, and that's the easiest one to look at is chain replication. You can see that in chain replication. We provide that in Paxos through the learners, but the learners are the complicated part because we still have to actually go and do, potentially, we have to go and do quorum reads. Because it might, that write might have just finished, but the knowledge of that write hasn't propagated through the system. So all the observers, regardless of where they are going to agree on the actual order of events, and it looks like there's just one copy of the data. This is very strong, it's very easy for people to reason about, except for the people who build the system itself. This is chain replication. It's Paxos, it's Raft, it's view-stamp replication. There's a whole bunch of these things. They are used for a very small class of problems. Sequential consistency relaxes this a little bit because what it says is you see the same interleaving, and that interleaving is in the same order it was locally, but that doesn't necessarily mean that it doesn't necessarily mean it actually happened in exactly the order you see it in. So it's the difference between local linearized and globally linearized. So linearizability is respecting real time, but sequential consistency respects the order in which things happen in the given program. Local consistency. So you won't see the operations on node X in any other order than anyone else will see them. So it now becomes possible to do a stale read. It's not going to happen all the time, but sometimes it does. In processors, we do this all the time. People will use what's called, they'll read a value in cache. And it's possible that the cache has actually changed. You can actually, I should rephrase that. It's possible the actual memory has changed. And that's considered to be an acceptable risk. It's kind of like the consistent cut model of the world. When you have multiple processors in a machine, and one of them is doing unlocked updates on the memory value, other parts of the system may continue to use their cache version of it. When we get into causal and eventual consistency, now what we're saying is a single client in causal will actually see their own writes. You write something, you read it back, you will see your write. You might not actually see everybody else's writes. But everybody will see that write in the order in which it occurred. Unrelated writes, no ordering guarantees. Nothing is linearized at this point. Not local operations, not global operations. In eventual consistency, you have to stop writing. You basically have to have everybody stop writing, and then you let the system settle, and eventually it reaches consistency. Hence the joke, never consistent. Eventual consistency means never consistent. It's always close, but it's never quite there. There's no bound on how long eventually takes. Some people are so impatient. It's only been a decade. You'll get there eventually. And you don't have any ordering guarantee even during that convergence window. The only time you have an ordering guarantee is when there's no outstanding rights and every read has been, all the rights have been committed. Well, gee, great, of course, that's the trivial case. Nothing's going on, it's easy to get consistency. So, eventual consistency is in fact some ways a lie, hence the joke and hence the red on the bottom of the slide. All right. So now let's do another one of those short exercises, which is you are reading a K from, this is our standard key value model. You're reading some key K from two different replicas a millisecond apart, and you get different values. Under which consistency models is this legal, and under which is it a bug?
It's not like C, like a specific subject.
It's just see the entire work.
Which one? Any of them? Could this happen?
In causal and eventual consistency, this can happen for sure. Okay. This
So,
is legal.
so he's arguing for causal and eventual. Anybody agree? Disagree? It's actually a trick slide.
It's legal in all of them.
That's correct. Why?
It's millisecond apart.
It's the problem is it's just a small tiny separation, but that's enough for somebody else to sneak a change in. That was the point I made before, which is if you want that level of consistency, you have to build a protocol on top of this to provide that guarantee. They literally have to do coordination between the clients to give you a guarantee that's going to be true across a time divide like that. Yep.
Couldn't then you say like every situation is legal because there's technically
That's the
always
problem
a
with this.
smaller- Oh,
That is the problem, right? So I spent all this time and I talked about strong consistency guarantees, and we sell strong consistency as being strong consistency, but from the perspective of somebody above that, the only thing they know is that everything that comes back is in order it happened, but that doesn't give them any guarantees between those events. So we spent a lot of time building a very complicated, very strongly consistent model, only to reach back and go, well, yeah, but if I wanted to update two different tables in two different databases, I can't do that. If I want to update the same value in the same database twice in a row, I can't do that. Not without an additional layer on top of that. See, a key value store is used as an example because in terms of databases, it's really simple. Get, put. Anybody know where that terminology shows up? Know anything about this? Sorry?
Rust.
Well,
No, rest.
rest is what it said.
Rust.
And where did rest get that from? Sorry.
HTTP.
Right, it's an HTTP. The HTTP protocol is get and put. So it's kind of like, oh, yeah, okay. So, we used to call those read and write, but now we call them get and put. It's the same exact idea, is that we get a value. Now in HTTP, the value that we get is based upon a URI. And that's the key value store. Literally the internet is itself a key value store that we manipulate. And it's got some pretty visuals around it as well. So that simplicity is beguiling, but then we build things on top of it that allow us to add the kind of temporal locking that we need in order to provide higher level protection for the complex operations that we really want to build. Causal and eventual consistency are much weaker, and they make building something on top of that that gives you two-phase commit style semantics a lot harder. Okay, so now this is going to go into this thing called the CAP theorem, which was proposed probably about the time you were born, 2024 2004, I think is the follow-up paper on it. Eric Brewer actually, he did it in a talk. It wasn't even like a paper or anything. He just literally gave this talk and laid it out this way. And he said, you get to pick between consistency and availability. So it's CAP, consistency, availability, and partition safe. And the reality is everybody has to choose partition safe because partitions are a function of the network that you don't control. So the only trade-offs there are how much consistency do you want versus how much availability do you want. And it's not a binary choice. You don't get to choose completely consistent with no availability or all availability and no consistency. But those four models, or those 4 points along the spectrum of consistency that I named are in fact different trade-offs between consistency and availability. So consistency here is literally how much linearizability do I want? Do I want global linearizability? Do I want local linearizability? Causal consistency isn't giving me linearizability anymore. It's still giving me something to reason about. And I might use that because I'm more interested in making sure that availability is satisfied. Availability is when can my writes proceed? When can my reads proceed? When can my gets and puts work? And again, it becomes a trade-off. If you have a quorum-based system, you have to have a quorum. Otherwise, when it goes below quorum, if you can't get a quorum, you have no availability. You lose availability. Now, often what people will do is they'll say, if I can't get a quorum, then I'll continue to serve the values that I saw last. But that isn't technically correct. That now means you can't actually do stale reads. So we'll call that Paxos Junior or something. Consistent partitionable systems are in fact the things that we've been studying. Paxos, Raft, chain replication. Well, I didn't really study Raft, but you can go read the paper. Maybe you'll decide that it's easier to understand than Paxos. I actually don't think it should be at this point, but I did give the link to the paper. Actually, I gave it, yeah, there's a copy of the paper in on Canvas. Available systems.
How do you know your minority side? Just counting doesn't work because there might be multiple partitions.
Only one of them can have a quorum. It's a good question. How do you know? Because you can have multiple partitions. And the answer is only one, at most one partition can have a quorum. But there's no guarantee that any of the partitions will have a quorum. So if you don't have a quorum, you can't take writes. And you can't confirm that the reads you're returning represent the quorum. Dynamo, Cassandra, Rearc are all the kinds of services that provide higher availability. But they do that by allowing nodes to continue answering exactly the questions I just said. I can't get a quorum, but I'm going to give you the last value I had for what you're asking for. Because it's more important for the system to give you an answer now, for whatever reason, for the use case, give you an answer now so you can proceed even if you find out later that answer was wrong. Anybody know anything else that likes to give out wrong answers? AI. Do you know why they do that?
They don't have a concept of right. They just make something.
They actually do have a concept of right and wrong, but it emerges as a byproduct. It's not a goal. It's a byproduct of the data over which they're trained, because most human data, in fact, is more truthful than not. But they are also trained to answer, and answer quickly, and answer authoritatively. And so when they don't know something and they have no tools available to obtain a correct answer, they will use their best guess based upon their training data. It's kind of like, you use that memory you have of a book that you read 2 years ago, and you promptly tell someone, this is what the book was about, even though it's complete BS, because your memory is itself false. They don't have eidetic memory. They don't remember everything. What they have is a statistical balance in there. When you look at how they, because you can actually see it. If you actually instrument them correctly, you can see when they are uncertain. Because it literally shows up as, there's a lot of different options in this probability space, and I don't know which one to pick. That's how it shows up. But when it comes to citations, interestingly enough, they've seen so many citations, they have no problems fabricating them. It doesn't even show higher energy spikes or anything. The entropy stays low because they've seen so many of them, they know exactly what the structure is, and it's short and easy to do. So there are things they can just make up. But that is exactly right. AI, great example. What's interesting is when you dig in underneath it and you realize it's not doing it because it's spiteful or evil, it's just doing it because that's what it was trained to do. If you train something to stroke your ego, you shouldn't be surprised when it starts stroking your ego. Make some good products, though. I bet nobody in here is young enough to have had a Tamagotchi. Yeah, it was a little fake pet, right? It was an electronic, yeah, right, okay, people, wow, okay, there we go.
From middle school, because it kept going on.
But the reason I brought it up as an example is a perfect example of a consumer product that was fun, and you bought it because it was completely useless, but it was fun. Well, that's kind of AI. Addict. So most real systems are not strictly one or the other. They tended to have a more complex set of trade-offs there. That's why I call that a spectrum. I put arrows on the side because I don't want you to think that those 4 points I picked are the only points on that spectrum. But that also means you're going to get people who say strong consistency. And you're going to say, okay, what does that mean here? Because if it's a salesman selling it to you, it means they want you to buy it. If it's a tech person telling that to you, they have a mental model of what it means, and you can ask them so then you know what it is you're buying. Whereas, if you're out buying a new car or a used car, they'll tell you whatever they think you need to hear in order to buy it. Kind of like AI. Maybe that's what they were trained on. They sent them to, used car sales school. In 2007, Amazon had a little problem. It's actually a really interesting case. How many of you have ever used Amazon? Have you ever purchased something from Amazon and had it shipped to you? Yeah, of course. It's the way we buy things these days. So why do you buy from Amazon and not from Temu? Since half the stuff on Amazon is just purchased from Temu. It's faster, right? You're paying for the convenience of being able to get this thing in something less than 6 months. Not that everything from Temu takes 6 months. Okay, so Amazon in 2007. So it's within your lifetime at least. Realized they had a problem with their shopping cart. When you click the button that says add this to my cart, it has to work. Now, there's lots of numbers around this. Amazon actually measures how much money they lose the slower it is for their IT infrastructure to respond to you. And they literally have numbers that say, you know, every 100 milliseconds costs us X number of dollars. And so it was more important for you to get that warm fuzzy feeling because it's in your cart now than it was to be absolutely sure that when you checked out that the item would be available. This is in fact when eventually consistent systems are just fine. But this is not a strictly eventually consistent system. At some point in the process, it will actually say, okay, you're buying this thing, now I really have to take it out of inventory. At which point it can come back and say, I'm sorry, that's no longer available. This is why you don't always want strong consistency. Odds are it's still going to be available when you check out. But if they take it out of inventory for everybody who puts it in their carts, they're going to lose sales because there are people who would have bought it but couldn't buy it because someone else who put it in their cart takes it out before they actually buy it. They chose add to cart, so they chose to make add to cart work even when they couldn't confirm things behind that. So you might see things that are not available, you might see old pages, but you will see something. Because if you get a 404 or you get a 500 error on that page, Amazon can't sell you something, and you're going to go someplace else. It's kind of a weird way to look at it, but it is in fact exactly why we talk about these consistency models and why having relaxed consistency models becomes important. But this is why they pay you the big bucks. This is an engineering decision. It's not a theoretical one. You have to actually make the decision. What am I willing to tolerate? In Dynamo, there's no leader, there's no fixed topology, and there's no consensus protocol. They literally just have n replicas. 3 is a magic number because, of course, you can always get simple quorums from a party of 3, 5, 7, 9, 11 because you can never have two quorums. Any replica can accept reads or writes. The coordinator forwards everything to all the replicas. And what are we playing for here now? The reality is most of the time these systems are up. All the time. And so we aren't really going to be worried about this. Yeah, it's going to be out of sync a little bit here and there, but that's okay with us. It now uses what's called a reader-writer quorum. It sends the writes out and it waits for a number of writers. And then it reads the back from them, and that number of writers and readers are used to create the intersection set, the quorum. And this was actually what was proposed in 1979 by Dave Gifford, where he said that you can do reader-writer quorums, so you can require more readers, so you wait until you can read the value from enough sites, or more writers to know when things have been updated properly. So the knobs, the things that you control, how many nodes are there, how many readers do you require, and how many writers do you require? As long as the number of readers and writers, assuming a weight of 1, Gifford actually I think did weighted, so you can weight them differently. As long as the weights add up, the number of readers plus the number of writers is greater than the number of nodes, you're fine. And what have we just recreated? Remind you of anything? Yeah, it's a quorum. You look at that and you go, oh, okay, great. Seen that before. Been there, done that, have a t-shirt. Back in lesson 10, lecture 10 I guess, we used the quorum intersection property. And so all we're doing now is just simply saying that for all quorums of readers and writers, a quorum of readers has to intersect with a quorum of writers in a non-empty set way. And this is, it was weighted voting, that's what I thought. Gifford 79, readers and writers had to be greater than the number of votes. So that's a generalization. If you just simply give everybody a weight of 1, then you can ignore the 1. You just do the readers plus writers has to be greater than the number of nodes. And that's exactly what Dynamo does. Dynamo uses uniform weight. The number of readers plus the number of writers that you contacted or heard back from is your quorum. And once you've read or written, you've heard from enough readers and writers, then you can proceed. You know that the change to the database is consistent at that point. No leader. You just sent some messages out and you did some reads. So you send a burst of writes, then you send a burst of reads. When the number of writes that get confirmed comes back, plus the number of reads confirmed comes back, and there's more of them than there are nodes, you're done. So we have readers and writers. We have 3 nodes, our replicas, and readers. So there's 2 readers, 2 writers, and the number of nodes is 3. So we get somebody who comes in here and writes, and as long as we can see 2 writes and one read, and it could be the same node that does both reads and writes, then we're done. Even though we still have a stale node out there, because someone else will have to do the intersection. And if they notice that one of the nodes is stale, they'll update it. That's typically what they do. They update it. So, oh, and of course we're going to sneak in versioning here, right? Why not? That allows us to tell staleness. So a reader has to contact 2 nodes. A writer has to contact 2 nodes. As long as the number of readers and writers, and here we see 2 and 2, so that was our 4, which is greater than the number that we need. So we have a guaranteed witness. We always have a quorum, and therefore we don't have an inconsistent behavior, even though we didn't coordinate anything. I mean, there's no proposals, there's none of that extra multi-round stuff with Paxos, and people influence this. But the beauty of it is, when you're willing to bend the rules and say, I don't really want to read a quorum, I just go read from a node and I get a stale value. Okay, perfect, time for the shopping cart. There were 3 items in inventory before he bought 2 of them. And so your order for 2 and his order for 2, and guess who's going to get their actual order filled? What would you do if you were implementing it?
Does it matter? Like, who gets it?
How would you implement is what I asked. Does it matter? Yeah, it matters to the person who ordered it. If she gets her order in before yours, and you find out that your order can't be filled anymore, you're going to be pissed. Who gets it? Who should get it? Which one of them is more deserving? Right, it's the first person wins. Easy. Ding, ding, ding. Okay, we didn't actually put the product in your cart. What we put was a token that says you can have 2 of these, and then you get up to the front, you give the chit to the checkout person, and they look and they say, "I'm sorry, we only have 1." And they bounce you, and they send you back to a page that says you can only have 1 now. Or they say, "Sorry, those are out of stock now, so you're going to have to wait. Are you willing to wait?" There wasn't any deep meaning to that particular question. It literally was this is a kind of engineering decision you might be called upon to make. What would you do? And the obvious answer is, well, of course. I'm going to give it to the first person to check out. Why am I going to do anything else? The second person might never check out. How many of you put things in your cart and left them there? And you get those nice little emails saying, this is still in your cart. But that's a different class. All right, so the tuning knobs that we have now give us different consistency models. If we start here, we get the strong consistency model, but If we're more interested in reads working, then we just simply need to have one reader. If we're more interested in writes working well, we have one writer, 3 readers. But then these are the fun ones, which are, well, we'll try and eventually we'll get there. This is an interesting one because this doesn't work. We didn't say readers plus writers is greater than or equal to n. It's readers plus writers are greater than n. The equals case is the problem because it means that we could actually have a partition and both of them could think that they have the correct value, and they don't. And underneath all of this is exactly the same quorum idea. This is just an expression of that quorum idea through a voting mechanism versus, I started with a set. Because I find that the set, the fact that you can actually draw the picture, you can show the intersection, it always makes sense. And then after that, everything we've seen, that's what you see. You just see the same intersection. You go, this is just the same thing. When reads plus writes greater than n, readers plus writers is greater than n, what do you do for the replicas that didn't see the write? Now you have to do repair. Now see, this is interesting because when we talk about Paxos, we don't really talk about how repair is done. And that's why when you sit down and you actually look at real implementations of things like Paxos or RAF or two-step replication or any of these other generalized consensus protocols, they sort of skip this, but they show in the implementation. How hard could this possibly be? You actually have to do what's called, you have to do repair. One way is to do what's called read repair, which means that when you find a reader with a stale replica of the data, somebody's behind the current sequence number, then you push a value to them. And typically what happens is you're piggybacking these repair mechanisms on top of message flows anyway, because you don't want to send extra messages for this. You want to design the protocol so that it has those extra messages so you can reason about it initially, but then you go in and you say, but I can just piggyback these. Because it's no different. If I take 2 messages that could have arrived at the same time, just put them together. I'm done. I have fewer packets that get sent. Anti-entropy means that, in fact, there's a background process that just simply randomly reads and writes. Or maybe it's not so random. Because remember, in Paxos, we have that log. You just randomly take things out of the log in an area where we haven't been able to confirm them for everybody yet, and we just go and confirm them with the nodes that haven't confirmed them yet. Try to make sure that they get updated. That's just a data structure. So the transactions, the idea is that in Paxos we had a log that we were building. But you can't store an infinitely long log. Eventually you run out of tape. So how do you know when it's okay to get rid of the old part of the log? Well, you build a data structure and you say, how can I tell when everyone else is already at least this far up in the log? When everyone is up at this point of the log, then I can truncate anything before that because everybody's already applied those changes. And that's actually what we're talking about here now. This is just a data structure mechanism. I know these nodes, you can keep it as a list. These are the nodes that I don't know if they have the right value. And then your background fixer comes along and says, hey, what's your value for that? Oh, you got the right value. Okay, what's your value for that? Oh, you've got the right value. Now, since it's mutating as we go, you're probably going to put a version number in there. So you know that their version number is greater than or equal to the version number that was placed in that spot in the log. And conveniently enough, it turns out that slots in a log are exactly the right version number. That gives you your linearization. There's this thing called gossip, these gossip protocols, where what happens is you just randomly send messages to other people going, psst, the value here should be. And surprisingly, it works pretty well. Gossip protocols are pretty cool to watch because they stochastically update in the network. So there's a whole statistical modeling behind these. Gossip protocols are often used with chat applications, for instance. Like non-centralized chat applications can work well because all of the nodes who are participating in a conversation can be sending messages to each other. And then you learn what their state is, they learn what your state is, and you can keep each other synchronized. Like a BitTorrent kind of scenario. So in read repair, what happens is we actually have a reader who reads from two locations, notices that they're out of sync, and then uses that as an excuse for repair. So it literally says, oh, I read these two nodes, they didn't agree with each other, so I couldn't use that value, or this, I can't rely on this value, but this one's behind that one, so let's get it updated. And you can literally propagate the update that way. In gossip protocols, you just pick other peers and you randomly send them messages. Now, I haven't really talked about the scale of efficiency here. In fact, the scale of efficiency here is to send these as multiple sets. You don't send a single change, what you send is a series of changes. And one of the common ways to build these kinds of changes is through a data structure called a Merkle tree. Another way of doing this, and I have been referring to this, is just versions. So we have versions, and we know what version a particular value is. And as I said, if you build this on top of Paxos, the logical thing to use for a version number is the slot in the log. You've automatically got your linearized versioning. The properties here in gossip protocols and any anti-entropy protocol is that it ends up being convergence through probabilistic means. It does actually work really well, but when you look at it, it's easy to say, wait a minute, somebody could literally fall behind and be behind forever. And the answer is, yeah, they could. It doesn't really work that way unless they get partitioned for a long period of time, but it could. Epidemic models. Anybody know what an epidemic model is? Anybody ever experienced an epidemic? Pandemic is just a different word for the same thing, isn't it? Pandemic means that 90% of the population got it. Epidemic means 10% of the population got it. Remember COVID? I mean, I actually used to have to explain to people why it is that they just can't see exponential. And I have a very stupid analogy that I'll use on you, which is if I give you a pond and I put one lily pad in that pond, and you know that that lily pad will turn into two lily pads the next day, and those two will turn into 4. And on day 48, the entire pond is covered with lily pads. How much of the pond is covered with lily pads on day 40? It's 1/256. And that's the part that people don't get about exponential growth. It's just, you're like, wait a minute, you spent 40 days getting to, what's that, 0.4%, and you spend the next 8 days getting to 100? Yeah, pretty cool. But the flip side of that is, that's why it's actually a very effective way of propagating changes through a distributed system. All you have to do is infect 2 other nodes, except that you're not infecting them, you're enlightening them, you're giving them the updated state of the world. This is cool. There is a heavyweight anti-entropy version which actually says, I'm going to just simply scan all the databases and bring them up to date. Now, if you think about that, the first time you scan everything, and the next time what you do is you say, what was the highest version number I saw last time? Because I don't need to worry about anything below that. So now I can update from there forward. These are expensive, they're thorough, they run in the background, they actually do work as well, but they're very heavyweight. But these are all solutions to the same problem, which is not everybody knows the current state of the world. How do I get them there? Because that was the dark side of the whole Paxos type of implementation is that Paxos gives us a quorum. We know somebody has the answer, but we don't know that everyone has the answer. And to make the system available, eventually you really do have to have everybody have the right answer. In version vectors, what we do is we use some sort of number. I'd suggested the Paxos log slot number, but you can use other schemes as well. You can use timestamps if you can get a universal time. We'll see a paper for that. So our replicas maintain vector clocks, and I did talk about vector clocks briefly weeks and weeks and weeks ago. Essentially think of it as, for a given node, this is the last version number I saw from them. For this given node, that's the last version number I saw from them. And remember that everybody else is sending me vector clocks from that they've seen as well. So my vector clock gets updated anytime I see someone else say they've seen a version number that's higher than the one that I've last seen. That means somebody else has already updated them. I don't have to update them. That's actually the pruning here. Because remember I said you're going to send it to people, but how do you know who to send it to? And the logical thing is to look through your vector clock and say, I'm going to send it to the nodes that the last time I talked to them, they had old state. There's no reason to send it to nodes where they've already seen the state that I have. So if they send me a vector clock with my current time on it, I'm not going to send them something back because they've seen everything I already know. So you take that vector clock, you increment your vector clock anytime you take a write, and on the read, then you take the component-wise max of the other ones you see. So if you get a vector that dominates the other, then you're done. In other words, all of the clocks in one are strictly greater than or equal to all of the clocks in the other one. I mean, if they're equal, then they're the same vector clock. If one of them has 2 entries that are ahead of yours and all the rest are the same, they win. But the hard part is when you actually have conflict, because the vectors don't have a clear ordering. And that's when you have to do conflict resolution. So Dynamo's answer here was, put everything in the cart. Conflict, put it all in the cart. If you took it out of the cart earlier and we're confused now because we saw an earlier version of your cart that had it in there, oh well, it came back. And you can take it out again. That's fine. This is the eventual consistency edge case that makes things a little more difficult. Like I said, you see it back in your cart. Has anybody ever seen an item appear back in your cart? It's really rare. But it can happen. You just take it out again. And the funny thing is that, of course, there's the human side of that, which is you might go back to your cart and see something in there that you thought you'd taken out and you went, huh, I probably just forgot to. Or I misremembered that. Probably consistent isn't a hard decision. It's not there's no one right answer here. So you have to decide. I use the shopping cart example. When it becomes monetary based, bank money, bank transfers between money accounts, that becomes a really big issue. One of the things that was very hard for the people who wanted to build digital cash systems for a long time was a problem called the double spend issue, where you can spend the same cryptocurrency more than once. And the whole reason that the blockchain became successful, and we will talk about blockchains because they're an example of Byzantine fault-tolerant distributed consensus protocols, was they solved that problem. They literally solved the problem of how do we prevent you from spending your digital cash twice. You can't do it. Now, it's a very heavyweight protocol to do that, but you can't do that. In a social media feed, you're on X, formerly known as Twitter, and you post something and it shows up 2 seconds later in somebody else's feed, you don't care. But inventory counting, not when you're putting things in the shopping cart, but when you're actually trying to see what you really have in stock, this becomes important because now this is a correctness issue. So each of these ends up having slightly different consistency models. We're not going to do this. I looked at this morning and I said, well, we might have enough time. We almost do have enough time. Let's see. Yeah. Think about it. I mean, it's still good. I left it in. I said, this isn't a bad exercise. It's something that you can use when you're trying to help yourself see if you understand the topics, what we're talking about. Because these are the kinds of issues that really will happen if you work with distributed systems. But I cheat and give you the brief answer. So you can pick a write quorum and a read quorum, and that will overlap. That gives you the overlap that you actually need. So that gives you a decision. So now you see a newer version from R2 in the older version from R3, but you're okay because you can take the newest one there. So when we did this with Paxos, we had to actually read and get a quorum, but we didn't have to do that here. In the second part, where we have non-overlapping quorums, then we can do a read, and that read will actually be satisfied using a stale value. And the only reason that didn't work was because we lost the whole quorum concept. We don't have a quorum anymore, we have a partition, and the partition gives us back different values. And that's not guaranteed. In fact, the hardest part about this really is that the inconsistency only shows up when the system itself is under stress. A lot of times you get away with this. Nobody notices that there's a bug until the bug becomes visible because it makes something actually perform incorrectly. Now these are the kinds of things that are fun to debug, but they will cause you to drink a lot. All right, so the last checkpoint here. In Dynamo, we use the number of readers plus the number of writers. It has to be greater than the number of nodes. For consistency, Paxos was using these two quorum models. Remember in flexible Paxos, we had different quorum, and that is very similar, right? It was different levels that we were comparing across. So the question is, are these the same? Or are they different? And 3 minutes, and that'll be our last. Our last hurrah.
For diving, it's all concept. But for Paxos, you actually.
Oh, I see what you're saying. What you're saying is that's not what let's work with. It just has to do with three quarters.
Yeah.
Yeah, like the way I was approaching it was
Yeah, like quorums don't cover the entire.
So thinking about it, just it's like value is less
All right. How many of you say they're the same? Great. So one of you who say is it's not the same, tell me why they're not the same. And this is why I need to actually bake cookies, because then people would have an incentive to answer. I had this conversation last Tuesday in the other class I'm teaching. I said, maybe I just need to offer cookies. Like, yeah. Food is an incentive. Like, great, I found an alternative to grades. I'll give you cookies instead. Were the cookies good? I think they're the only people who had them. Well, they were in 436C. I gave cookies last time. Were they good? Nice and good. Well, there we go. Devin the fake praise, crushing my dreams. You know, I find I won't be giving up my life as a bad instructor. I can just because I'll be a worse cookie maker. Okay, so, and of course you can always just flip to the next slide and see. No, they're not the same. So even though Dynamo's mechanism actually does force that there's a read overlapping with the write, it doesn't actually guarantee the ordering of concurrent writes. Because remember, in that case of multiple readers and one writer, you had other writers. They could have already written this thing. So it is not the same as Paxos. See, the one extra thing that Paxos provides us with is that guarantee that everything's linearized. The writes are linearized, so therefore the reads are linearized. But we don't get that from quorum voting, from the voting mechanism, because the voting mechanism doesn't order things. It just guarantees that we have a valid read. So it's that extra step there. Damn it. Here I was thinking that we were going to be able to come up with some really great scheme that was going to get us out of having to write Paxos. But the reason I still have to teach you Paxos is because sometimes you actually need ordered writes. Here, no, it can actually conflict, and you'll do last writer wins. You will resolve it in some way. But the reason I had to go through the whole discussion about repairing is because repairing is a reality in a quorum system, in this read plus write quorum system, not the Paxos quorum system. All right, so this is the question for you to think about, which is you have a client that's using your Dynamo store. They're reporting stale reads during normal operations without partitions. Where are you going to go look? actually not going to answer this one. I'm going to let you think about that, because this is really the whole point of the conversation, which is, if you want to know that you understand it, think through this and say, I think I know where I would go looking. I think I would try to I could figure out why they were getting stale reads in a system that shouldn't be experiencing stale reads. And then when you're building things, anybody building in a replicated database or anything? Okay, so when you're building things, think about observability. It's really important. It's so hard to debug distributed systems anyway. I mean, it's literally a research problem still. A quorum. So think, how would you actually log these things in your system? These are the kinds of observability data that you need in order to figure out where the bug is. You can have a complete TLA plus model, all model checked, and oh yeah, it's going to work. And then you have to actually implement it in Rust, and suddenly you're like, how do I know my Rust implementation is actually the model? And that's why you still need the observability. And of course you're writing in Rust, right? And maybe blank stares. Of course not. What are you writing in? Go. Okay, fine. Go ahead and be old. Wow. The cool kids use Rust. Go is like so 2000s. So what we talked about today is that there's no single type of consistency. Consistency is a spectrum, and you get to pick a spot along that spectrum. And I picked 4 to lay out there, and I gave them labels, but the reality is that it's a continuous spectrum. There are lots of different points on that aren't quite any of the labels I gave you, but they're still on that spectrum. So, we can all be on the spectrum. The key thing to think of here is that the farther you are up towards linearizability on that spectrum, the harder it is to build, the more expensive it is to guarantee. And people work very hard at trying to drive that complexity down. I mean, at this point, Amazon S3 is providing strong consistency. And that for 20 years, has been a weekly consistent system. And suddenly they said, hey, look, we've now got actually strong consistency. Whoa, that's a big change. I don't know what they did. And they said, and they're claiming that it didn't reduce performance. So when you have a partition, you can either choose consistency or availability. Dynamo is leaderless. It does have this tunable reader plus writer quorum overlap. We talked about repair. We talked about how quorum overlap is necessary but not sufficient for strong consistency. Paxos also linearized the order of our write operations, and that was what was critical. So in quorum, in the reader-writer quorum, we can actually read stale data. That's essentially the point. There could be writes that we haven't serialized against yet. And so next week, we're going to be talking about Byzantine failures. This is where a node lies. It doesn't mean that it's malicious. A node with a faulty piece of memory can cause messages that are corrupted or aren't quite right. And how do you deal with that? Especially when you're trying to build a distributed fault-tolerant system and one of your nodes is broken and sending out, like, garbage. Oh, here's another pile of poop for you. Please, replicate it. Have a nice day. That doesn't work. So how are we going to deal with that? And that's fun because that's a different direction in the same space. Because all of a sudden we have to worry about another class of failure. Isn't it interesting taking a class that's all about failure? And how to deal with it. This is life prep, people. Not that any of you are going to fail. Byzantine Generals is actually the motivating paper for next week's discussion. It should be on. I know it's in the files. I think it's linked into the module, but if it's not, I will link it into the module.
All right, I will see you next week. And the week next week is week 9. So it's 2 weeks to capstones. So you might want to be thinking about it. Sorry,
3 weeks today. 3 weeks. 3 weeks. Or 3 weeks tomorrow. Yeah, it's the 27th is due.
All right.
What were some other capstone projects like in the past year?
I gave you guys exemplars. I thought I gave you exemplars. Maybe I only gave them for the project.
Your project, I think it was project one.
Let me go find some exemplar projects.
Like what would you like everything's already done, so like
Actually, it's not already done. So like ideas, you can go and you can build something like, let's just say flexible paxos or fast paxos. Both of those are very interesting. And there aren't really very many systems built on top of those. I mean, there's nothing wrong. It's just simply building, one of the last projects in the DS lab. It's hard. Get that working on your own is still really hard because it's too basic and with reconfiguration.
That doesn't